March 4, 1889. South Fork of the Payette River, Idaho Territory. Late winter precipitation logs for central Idaho show 28 to 32 inches of snow deposited in a single 24-hour period, with water equivalents above 3.5 inches, one of the densest March accumulations recorded in the basin before 1900. The weight-sheared, half-rotted lodgepole from the upper slopes. A 2,200-pound trunk slid downslope on a freeze-rain crust and hit a cabin's front porch. Most frontier porches were rigid, posts spiked directly into 10 to 12-inch sill logs, transferring lateral impact into the wall. This cabin had a different system, a sacrificial porch built with slip-jointed posts, shallow pockets, and wooden pins engineered to shear. The tree shattered the porch. The front wall remained untouched. The measurements, not the myth, explain why a structure built to fail protected what frontier builders valued most. Frost-rimed rafter. Evidence of thermal stress patterns documented in Army engineer reports, Payette Basin, Idaho Territory. 1880 through 1889 patterns of settlement and survival. Frost formed on the inside of cabin rafters across the basin each winter, thick enough by March to scrape with a thumbnail. Hay twist fires, bundles of dried grass twisted tight and burned slow, provided heat in cabins where cordwood had run low. By early March, most homesteads were burning the last quarter of their winter fuel supply. The Signal Service climate tables from the 1870s and 1880s defined baseline snow load expectations for the region. 12 to 20 pounds per square foot was typical for the Payette drainage. Builders planned for those loads. They cut 10 to 12-inch lodgepole pine for wall logs, notched the corners using saddle joints, and laid dirt floors that packed hard by midwinter. Porches were added as needed, simple platforms extending 4 to 6 feet from the front door, built with posts spiked directly into the sill log. The system worked in average winters. The problem was that spring storms in the basin were not average. Late winter precipitation events regularly exceeded 30 pounds per square foot. Wet snow, heavy with moisture content, accumulated faster than it could compress or melt. The weight bent rafters. It crushed lean-to roofs. It loaded the upper slopes with mass that eventually had to move. United States Army engineer reports from Fort Boise, filed between 1878 and 1887, documented multiple spring snowdrop failures, sheds, roof extensions, and covered walkways collapsing under loads that exceeded design assumptions. The pattern repeated across the territory. Structures built for typical conditions failed during extreme events. Indigenous construction methods offered a contrast. Shoshone and Northern Paiute groups in the region built seasonal structures, using flexible pole frameworks. These frames absorbed wind shear and snow load through controlled deflection rather than rigid resistance. The poles bent, the structure survived. When a component failed, it was replaced. The principle was straightforward. Manage force through flexibility, not strength alone. Frontier builders rarely adopted these methods. The cultural gap was wide and time pressure was constant. Homesteaders needed structures that could be built quickly, using familiar techniques with tools they already owned. Rigid construction met those requirements. The consequences appeared later. Typical cabin porches were assembled in an afternoon. Posts were cut from nearby lodgepole stands, round logs 6 to 8 inches in diameter, sometimes less if good timber was scarce. The builder would spike the base of each post directly into the front sill log, using hand-forged nails if available, or wooden pegs if not. Stringers ran between the posts, supporting a plank deck. A simple roof extended from the cabin wall to shed rain and snow. The design transferred all lateral force directly into the primary structure. When a falling branch struck a post, the impact traveled through the spike connection into the sill log. When stock animals leaned against the porch for warmth during cold nights, the pressure bent posts and stressed joints. When spring thaw sent waterlogged deadfall downslope, the impact had nowhere to go but into the cabin wall itself. Field reports showed the result. Front sill logs cracked along the grain. Door frames twisted out of square, jamming doors shut. A dangerous failure in structures where egress could mean the difference between survival and death by fire or animal attack. Walls bowed outward at the base, compromising the structural integrity of entire sections. The problem was not ignorance. Builders understood that rigid connections transmitted force. The issue was priority. A homesteader arriving in spring needed shelter before winter. A trapper establishing a line camp needed basic protection within days, not weeks. Speed and simplicity took precedence over long-term structural analysis. In many documented cases, the storm did not break the cabin. The porch did. Iron hinge with wind-worn grit. Symbol of supply chain fragility in remote settlements. 1880 through 1890. Idaho mining corridors and trapping routes stretching from the Boise Basin north through the Salmon River country. Iron hinges ground with accumulated grit during winter months when wagon traffic stopped and resupply became impossible. The dust that settled into every moving part was not cleaned. Water was frozen and oil was reserved for firearms and tools more critical than door hardware. The hinges functioned, but roughly, each swing marking the passage of isolated weeks. Frontier logistics operated on schedules that were reliable until they were not. Store ledgers from Idaho City and Placerville, preserved in Idaho Territorial archives, show that iron spikes and cut nails were expensive commodities, often repurposed from abandoned structures or salvaged from packing crates. A pound of square-cut nails cost 15 to 25 cents in the 1880s, roughly equivalent to a day's wages for common labor. Wooden pegs, hand-carved from hardwood scraps, cost nothing but time and were therefore preferred for non-critical connections. Winter freight delays of 4 to 10 weeks were typical. Wagons carrying kerosene, flour, coffee, and hardware left Boise on schedules that assumed passable roads. When early snows closed the passes or spring mud made trails impassable, settlements went without. Kerosene shortages were frequent enough that homesteaders rationed lamp use, working by firelight or moonlight to preserve fuel for genuinely dark nights. Cabin fuel consumption was documented with precision born of necessity. A typical 10-foot by 12-foot cabin burned 12 to 18 cords of wood per winter, roughly 400 to 550 cubic feet of split, seasoned cordwood. That represented weeks of labor, locating standing deadwood, felling it, bucking it to length, splitting it, and hauling it to the cabin site. Green timber cut from living trees burned poorly and generated creosote buildup in chimneys, but homesteaders often had no choice when deadwood supplies ran short. Porches were built quickly because time was a more constrained resource than timber. An experienced builder could frame and deck a simple porch in an afternoon, using the nearest accessible lodgepole stand. The posts required no special preparation, bark left on, no seasoning time. Stringers were rough cut. Decking was nailed down with whatever fasteners were available. The structure was functional within hours. Building manuals of the period, such as Hodgson's 1872 treatise on frontier construction, emphasized tight joinery and proper seasoning of timber. The recommendations were sound. They were also largely ignored in practice. Trail camps, trapping cabins, and first-year homesteads were built under time pressure that made careful joinery a luxury. Floating elements, components that sat in place by gravity or friction rather than being rigidly fastened, appeared in temporary structures because they were faster to assemble and easier to repair. The tools available to frontier builders were simple and multi-purpose. A broad axe for hewing logs flat, a crosscut saw for bucking timber to length, augers in 1 to 1 1/4 inch diameters for drilling holes, a draw knife for shaping and smoothing, a maul and wedges for splitting, no specialized equipment, no powered tools. Every structure was built by hand, using techniques that could be learned through observation and practice. The contrast between manual recommendation and field reality was stark. Manuals prescribed mortise and tenon joints, seasoned lumber, and engineered load paths. Field. Construction used lap joints, green timber, and intuitive assembly. The gap between ideal and actual was not a failure of knowledge. It was an adaptation to constraints. The more rigid the porch, the more likely the front wall failed. Builders did not yet understand why, but the pattern was emerging in structures across the territory. Crushed grass pattern. Physical evidence of stock pressure against winter structures, South Fork drainages, Idaho Territory. 1880 settlement patterns across lodgepole benches and creek bottoms. Crushed grass surrounded the front posts of cabins where cattle and mules had rubbed against the wood for warmth during cold nights. The pattern was consistent enough to appear in multiple photographic records from the period. Flattened vegetation in an arc matching the height and reach of large animals seeking any break from winter wind. The marks were not decorative. They were evidence of lateral forces applied repeatedly to structures never designed to resist them. United States Geological Survey topographic sheets from the 1880s show that most homestead sites in the basin occupied benches with slope angles between 18 and 32 degrees. The locations offered advantages: proximity to water, drainage away from the cabin floor, and access to timber. They also created hazards. Anything moving downslope, water, snow, or deadfall, accelerated as it descended. Lodgepole pine dominated the forest composition at elevations between 5,000 and 7,000 feet. The species grew straight and tall, making it ideal for cabin construction, but it was also vulnerable to endemic beetle infestations that weakened stands over time. Forest Service retrospectives compiled decades later identified cyclical patterns of infestation and decline. By the mid-1880s, many stands contained high percentages of standing dead timber, trees still vertical but with compromised root systems and brittle wood. Spring weather patterns added the final variable. Freeze-thaw cycles turned snow into ice crusts. Rain falling on frozen ground created lubricated surfaces. Saturated soil lost cohesion. The combination transformed slopes into chutes where loose objects accelerated with minimal friction. Lateral force estimates, reconstructed from engineering analysis of documented incidents, suggest that falling limbs generated 400 to 1,100 pounds of impact depending on mass and velocity. Drifting stock animals pressing against posts for extended periods applied sustained pressure in the same range. Both forces exceeded the shear capacity of typical porch connections. Rigid porches transmitted those forces directly into the cabin's front sill log, the horizontal timber that formed the base of the front wall. The sill log was load-bearing, supporting the entire front wall and often the roof framing as well. Damage to the sill compromised the structural integrity of the entire facade. Idaho newspaper notices from the 1880s document the results. The Idaho Statesman, in an 1886 edition, referenced a homestead where the front room was jammed by tree drop, requiring the sill to be replaced before the door could open. An 1887 notice from the Boise Basin mentioned a lean-to carried off in the spring thaw when a deadfall struck the support posts. The language was matter of fact. These were not catastrophic failures worthy of extensive coverage. They were routine incidents, expected hazards of frontier life. That normalcy is itself revealing. Builders anticipated damage. They planned for repairs. The question was not whether porches would fail, but when and how much collateral damage they would cause. Multiple hazard sources converged on a single weak point: snow load from above, wind pressure from the side, stock animals from ground level, falling timber from upslope. Each pathway led to the same structural component, the front sill log. And because most porches were rigidly attached to that sill, every impact became a threat to the primary structure. No matter the source of the force, every hazard found the same vulnerability: the connection between porch and cabin. The solution would require rethinking that connection entirely. Snowbent rafter fragment, physical evidence preserved in Fort Boise Engineering Archives, Idaho Territory, 1881 through 1888. Multiple documented structural failures across settlement zones. Snow-bent rafters creaked under load before collapse, a warning sound that gave occupants seconds to evacuate if they were awake and alert. The failures happened under ordinary conditions, not rare catastrophic storms. This was not extreme weather overwhelming exceptional structures. This was routine weather defeating inadequate design. Army engineer reports cataloged the incidents with bureaucratic precision. A shed at Fort Boise collapsed under spring snow load in April 1882, injuring no one but destroying stored equipment. A lean-to addition to a line cabin near the Payette Lakes folded forward in March 1884, tearing away from the main structure and leaving a gap that admitted wind until repairs could be made. A covered porch at a mining camp near Idaho City broke free during a wet snow event in 1885, the posts shearing at ground level and the entire platform sliding downslope. The pattern repeated with enough frequency that territorial newspapers stopped reporting individual incidents unless they involved injury or significant property loss. Porch failures became background noise, expected, unremarkable, part of the cost of living in snow country. Technical specifications for typical porch assemblies were straightforward. Posts were 6 to 8 inches in diameter, cut from round lodgepole, with bark removed or left on depending on the builder's preference and available time. The bottom of each post was either pointed and driven into the ground or flattened and spiked to the sill log. Spikes, when available, were 8 to 12 inches long, driven at an angle to maximize holding power. Stringers, the horizontal beams running between posts, were 3 to 4 inches thick, notched into the posts or simply nailed in place. Decking consisted of rough-cut planks laid across the stringers and fastened with whatever nails could be spared. Roofs, if present, extended from the cabin wall using rafters that either rested on the stringers or were spiked to a header beam above the door. The loads these assemblies faced frequently exceeded their design capacity. A wet snow event depositing 2 feet of accumulation at 30 pounds per square foot generated 1,500 pounds of load on a modest 8-foot by 4-foot porch roof. Falling timber from upslope could deliver impact forces of several thousand pounds. Stock animals leaning against posts applied sustained pressure that bent wood and loosened connections over time. The failure mode was predictable. Rigid connections transferred force into the sill log. The sill, constrained by the wall logs above and below, could not deflect. Stress concentrated at the connection point. The wood split along the grain, or the spike tore free, or, in the worst cases, the sill cracked, creating a structural discontinuity that weakened the entire front wall. Repair was costly in time and materials. Replacing a damaged sill log required jacking up the front wall, removing the compromised timber, fitting a new log, and rechinking the joints. The work took days and required help. In isolated locations where neighbors were miles apart, that help might not be available. The failures were not surprising. Builders expected them. What they had not yet developed was a solution that prevented the failure from propagating into the primary structure. Loose-pin drying rack, design precedent documented in trapping journals, trail camps, line cabins, and indigenous seasonal encampments across Idaho and Montana Territory. 1870 through 1890 construction records. A drying rack pattern appeared in multiple trapping journals from the 1870s. A simple framework of vertical poles set into shallow sockets, held in place by their own weight and by horizontal crossbars that rested in notches. The poles were not spiked or pegged permanently. They could be lifted out and replaced if damaged. The structure was temporary by design, expected to be rebuilt each season. The principle was flexibility through sacrifice. If wind knocked the rack over, no permanent structure was damaged. The poles could be reset in minutes. If a bear investigated the drying fish and destroyed the frame, the loss was contained. The method appeared in contexts where builders expected repeated failure and designed for easy recovery. Shoshone and Northern Paiute groups in the region employed similar principles in their seasonal pole structures. Frameworks for windbreaks and summer shelters used flexible lashings rather than rigid joints. The poles could deflect under wind load without breaking, and individual components could be replaced without dismantling the entire structure. The engineering was intuitive rather than calculated, but the principle was sound. Manage force through controlled compliance rather than absolute resistance. United States Army field manuals from the 1870s described temporary structures for campaign use, including sheds with give-way braces, angled supports designed to fold under extreme load, protecting the primary structure by failing first. The concept was explicit: sacrifice a replaceable component to preserve the essential framework. Engineers understood the principle. It simply had not migrated to civilian construction. Technical specifications for breakaway connections existed in the material properties themselves. Wooden dowels, sized between 5/8 and 3/4 of an inch in diameter, sheared at predictable loads depending on species and moisture content. Hardwood pins made from oak or maple sheared at 350 to 700 pounds. Softwood pins from pine or fir sheared at lower thresholds. The variation allowed builders to tune the failure point by selecting appropriate materials. Slip sockets, shallow pockets in which posts rested without being permanently fastened, appeared in small utility structures across the frontier. Fish drying racks used them. Hay storage frames used them. Equipment sheds used them. The socket depth was typically 1 to 2 inches, just enough to keep the post aligned, but not enough to lock it in place. If lateral force struck the post, it would tip or slide out of the socket rather than breaking or transferring the load to the foundation. The technology was present. The knowledge was available. The methods had been proven in multiple contexts. What was missing was the application to cabin porches, structures that frontier builders treated as permanent rather than sacrificial. The gap between available knowledge and actual practice was cultural as much as technical. Porches were seen as extensions of the cabin, not as protective buffers. Builders invested effort to make them strong, not to make them fail safely. The shift required rethinking the porch's role in the system. The technology existed. It simply had not been applied to the problem. Worn auger shavings, physical remnant of precision socket drilling, reconstructed standard practice, Idaho Territory, 1880s. Auger shavings curled beside a sill log, pale spirals of fresh wood marking where pockets had been drilled for post bases. The shavings were the visible trace of deliberate engineering, shallow sockets cut to precise depths, sized to hold posts loosely rather than lock them tight. The specifications for a sacrificial porch diverged from standard construction in every detail. The differences were subtle but critical, each element designed to control how and where failure occurred. Post pockets were drilled 1 1/4 to 2 1/4 inches deep, enough to stabilize the base of the post, but shallow enough that lateral force would tip the post out rather than snap it. The pocket diameter was cut to match the post diameter plus 1/4 inch, creating minimal clearance. Too tight and the post would bind. Too loose and it would shift during normal use. Posts themselves were selected from lodgepole pine in the 5 to 6 inch diameter range. Green timber was preferred over seasoned because moisture content affected shear characteristics. Dry wood shattered under impact, green wood deformed predictably. The moisture made the failure mode more gradual, giving the structure time to dissipate energy before a catastrophic collapse. Dowels, wooden pins that reinforced the post-to-pocket connection, were critical to the system's performance. 2 opposing pins were driven through each post just above the pocket depth, angled downward at 15 to 20 degrees. The angle was essential. Vertical pins would shear cleanly under lateral load, but provide no directional bias. Angled pins guided the post's motion outward and upward, away from the cabin wall, when force exceeded the pin's shear capacity. The dowels were sized between 5/8 and 3/4 of an inch, made from hardwood when available, oak or maple, or from dense sections of lodgepole heartwood when hardwood was scarce. Each pin was calculated to shear at 350 to 700 pounds, depending on species and grain orientation. 2 pins per post meant the system would begin to fail at loads between 700 and 1,400 pounds. well above typical wind or stock pressure, but well below the impact force of falling timber. Header beams ran horizontally above the door, connecting the tops of the porch posts. In standard construction, these beams were substantial, 6 inches or more in thickness, to prevent sagging. In sacrificial construction, the header was deliberately undersized, 3.5 to 4 inches thick. The reduced cross-section meant the beam would fold under vertical load before that load could transfer into the cabin wall. Roof framing followed the same logic. Rafters were set at a 2 to 12 pitch, just enough slope to shed water, and attached to the header beam and cabin wall with minimal fastening. Light pegs or a few nails held the rafters in position during normal use, but would release under stress. The goal was to allow the roof to collapse forward and downward, away from the cabin, rather than pulling the cabin wall outward. Decking was loose-laid or lightly fastened. Planks rested across the stringers with enough friction to stay in place during foot traffic, but not enough nailing to create a rigid diaphragm. This prevented the deck from acting as a structural membrane that could transfer lateral forces back into the sill log. Every element was engineered to lose. The porch was not a structure meant to stand indefinitely. It was a controlled failure mechanism designed to absorb impact and collapse in a direction that protected the cabin behind it. Store ledger fragment. An 18 CPI for 2-inch auger pins, hard maple, Idaho Territory camps and settlements, 1880s economic and labor analysis. A ledger line from a supply store in Silver City recorded the purchase of hardwood pins for auger work, 18 cents for a set of maple dowels sized at 2 inches in length. The notation was routine, one entry among hundreds tracking the small transactions that sustained frontier life. The cost was modest but not trivial, equivalent to an hour's wages for skilled labor. Labor time for constructing a sacrificial porch was 10 to 14 hours for a practiced builder working alone. The timeline assumed pre-cut posts and seasoned timber for dowels, with all tools in good condition. An inexperienced builder might require twice that time, especially for the precise auger work needed to create uniform pockets. Material volume was minimal. 1/10 to 2/10 of a cord of timber supplied posts, stringers, rafters, and decking for a standard 8-foot by 4-foot porch. The wood came from the same lodgepole stands used for cabin construction, requiring no special procurement. Dowels could be whittled from scrap hardwood or dense pine heartwood, adding negligible material cost. Tool requirements were basic: a broad axe for rough shaping, a crosscut saw for bucking logs to length, a draw knife for smoothing surfaces and creating the slight tapers needed for post bases. An auger, 1¼ inches for pocket drilling, 5/8 inch for dowel holes, and a wooden mallet for driving pins. No specialized equipment, no materials unavailable to a typical homesteader or trapper. Winter constraints affected construction timing. Frozen ground made socket drilling more difficult. The auger bit would skate across ice-hardened sill logs until the surface was scored deeply enough to catch. Low daylight hours reduced working time to 6 or 7 productive hours per day in December and January. Tool wear accelerated in cold weather as metal became brittle and wood handles contracted, loosening heads. The comparison between rigid and sacrificial porches was instructive. Rigid porches were faster to build, 3 to 5 hours for a simple platform, but carried high downstream costs. When damage occurred, repairs often required sill log replacement, wall realignment, and door refitting. The work took multiple days and required assistance for lifting and positioning heavy timbers. In remote locations, that assistance might not arrive for weeks. Sacrificial porches required more initial labor but eliminated catastrophic repair scenarios. When the porch failed, as designed, the damage was contained. 2. Replaceable components. A set of pre-cut posts stored under the cabin or in a shed allowed rebuild in less than 10 hours. No jacking, no wall work, no waiting for help. The mathematics favored investment in initial construction quality. One day of careful work during the building phase prevented weeks of difficult repair work during the season, when every day of labor had to be weighed against other survival tasks: hunting, fuel cutting, equipment maintenance, and travel before snow closed the passes. Frontier builders operated within severe time constraints. Every hour spent on one task was an hour unavailable for another. The decision to build a sacrificial porch represented a calculated trade. Accept higher initial labor cost to reduce future catastrophic loss. The calculation required looking beyond the immediate season to the structure's multi-year lifespan. One day of work could protect a decade of wall integrity. That ratio, 10 hours of labor preventing hundreds of hours of repair, justified the investment for builders who understood the long-term costs of inadequate design. Field photograph fragment. Lean-to, angled outward post-thaw, circa 1886, Salmon River, Big Wood River, and Boise Basin drainages. 1870s through 1880s incident reconstruction. A photograph preserved in early Forest Service archives shows a cabin with a porch leaning outward at a 15-degree angle, separated from the front wall but not completely collapsed. The image was catalogued as evidence of structural failure, but the notation missed the significance. The porch had failed without damaging the cabin. The separation was not a flaw, it was successful performance of a sacrificial system. Snowdrop incidents, the term used in period documents for roof loads sliding or collapsing under wet spring accumulation, recurred across the basin settlements. A typical event involved 20 to 30 inches of wet snow accumulating on a low-pitch roof, then releasing as a coherent slab when temperatures rose and meltwater lubricated the interface between snow and roof surface. The mass slid forward onto porch roofs, delivering vertical and forward loads simultaneously. In rigid porch systems, the impact bent posts, split header beams, and drove the entire assembly backward into the front wall. In sacrificial systems, the header beam folded, the dowel sheared, and the porch roof collapsed forward onto the ground. The difference in outcome was categorical. One damaged the cabin, the other did not. Stock impact evidence appeared in multiple forms. Sheared dowels recovered from porch sites showed characteristic fracture patterns, clean breaks across the grain at the expected shear plane with no splintering or crushing that would indicate overstress or defective material. The pins had performed exactly as designed, failing at predictable loads to prevent force transmission to the sill log. Roof load collapses demonstrated the same principle. A porch beam that folded under a 1,000-pound snow load protected the cabin wall from that same load. The beam was replaceable, a day's work to cut and install. The front wall was not replaceable without dismantling and rebuilding the entire structure. Idaho newspaper archives contain oblique references to these events embedded in notices that were not recognized as documenting a successful design pattern. An 1887 report mentions a homestead where the front porch was carried away in the thaw, but the cabin stood sound. The phrasing treats the porch loss as unfortunate. A structural analysis treats it as intentional. Reinterpretation of historical incidents changes their meaning. Events labeled as failures in period documents can be recognized as successful sacrificial performance when examined through the lens of protective system design. The porch that collapsed prevented the cabin from being damaged. The loss was contained, predictable, and easily remedied. The pattern was visible across multiple seasons and multiple locations. Porches failed regularly, cabins behind sacrificial porches remained intact. The correlation was present in the historical record, waiting for someone to recognize it. Trapping journals from the Salmon River drainage mention platforms that give way when struck in descriptions of line cabin infrastructure. The language is casual, suggesting the behavior was expected rather than surprising. Ranch records from the Big Wood River area reference replaceable post sections in corral and shed construction. The same principle applied to livestock facilities. The method worked long before the March 4, 1889 event that would become its most dramatic demonstration. The knowledge was distributed across the territory, embedded in structures that performed their protective function without fanfare or formal documentation. The record shows the method worked. It simply had not been recognized as a unified system until a single event made the engineering impossible to ignore. Ice-glazed pole stack. Physical evidence of freeze-rain conditions March 4, 1889. South Fork of the Payette River, Idaho Territory. Ice sheen coated the stacked poles beside the cabin, each log wrapped in a transparent glaze left by overnight freeze rain. The surface caught morning light and reflected it in brittle sparkles, beautiful and treacherous. The glaze was thin, perhaps an eighth of an inch, but it transformed every surface into low-friction pathways for snow and debris. Climate records for the event, reconstructed from Signal Service observations at Boise and interpolated for elevation, document 28 to 32 inches of wet snow accumulation in a 24-hour period beginning the evening of March 3rd. Water content exceeded 3.5 inches, roughly 11% water by volume, indicating snow of exceptional density. Normal powder snow measured 3 to 6% water content. This was slush, heavy, and cohesive. Wind patterns during the storm were moderate, 10 to 15 miles per hour from the southwest, not strong enough to prevent accumulation, but sufficient to load leeward slopes with drifted mass. The South Fork drainage runs northeast-southwest, creating northwest-facing slopes that collected transported snow in addition to direct precipitation. Temperature records show a crucial sequence. Evening of March 3rd, 28 degrees Fahrenheit, with light rain transitioning to snow. Midnight, 24 degrees. Dawn on March 4th, 18 degrees. The freeze-thaw-freeze cycle created layers within the snowpack, ice lenses separating snow strata, each layer creating a potential failure plane. Slope analysis from geological survey data shows the lodgepole bench above the cabin sat at angles between 18 and 30 degrees, within the range where snow slabs could move under their own weight if triggering conditions aligned. The slope was not steep enough to avalanche spontaneously under most conditions, but the freeze-rain crust provided the trigger, a lubricated surface that reduced friction below the threshold needed for stability. Root rot in standing deadfall was documented in the region. The 1888 growing season had been unusually dry, stressing trees and creating conditions favorable for bark beetle infestations that killed timber but left it standing. By March 1889, many trees on the upper slopes were dead but vertical, their root systems weakened by decay and frost heave. The combination of factors, wet, heavy snow, ice crust, moderate slope, and compromised timber, created maximum lateral load conditions. The snow mass was dense enough to carry significant momentum. The ice crust reduced friction to near zero. The slope provided gravitational acceleration. The dead timber was ready to release from failing roots. Weather analysis from the period identifies March 4, 1889, as part of a larger pattern of late winter storms that affected the entire northern Rockies. Similar events occurred in Montana and Wyoming the same week. The storm was not anomalous. It was an example of conditions that occurred somewhere in the region every few years. The significance was not that the storm was unprecedented, but that it tested structures under precisely the conditions that sacrificial design was meant to address. High lateral load from an unpredictable direction, delivered without warning, exceeding the capacity of any rigid system. Everything aligned. Snow load at the upper limit of historical range. Ice crust reducing friction. Slope angle in the critical zone. Timber compromised and ready to fail. A cabin with a porch designed to absorb and dissipate lateral impact through controlled failure. The test was about to begin. Splintered dowel fragments. Physical evidence recovered post-impact March 4, 1889. Same location, mechanical reconstruction of impact sequence. Splintered dowel fragments were recovered from the debris after the impact, clean shear breaks across the grain at the expected failure plane, with wood fibers separated rather than crushed. The fracture pattern confirmed that the pins had performed as designed, failing at loads within their engineered capacity rather than being overloaded catastrophically. Mass estimation for the fallen trunk, based on lodgepole pine density and measured diameter, yielded approximately 2,200 pounds. The tree was roughly 40 feet in length and 12 inches in diameter at the base, a mature lodgepole in the mid-range of typical basin specimens. Dead weight, without foliage or moisture, but substantial. Velocity estimation required analyzing the slope profile and surface conditions. The trunk likely began moving slowly as root failure allowed it to tip, then accelerated as it slid on the ice crust. Terminal velocity on a 25-degree slope with near-zero friction reached 12 to 15 miles per hour, roughly 20 feet per second, over a descent distance of 70 to 90 feet. Impact force calculation from these parameters exceeded the capacity of any rigid porch system by a factor of 3 to 5. A standard porch with posts spiked to the sill would have transmitted between 6,000 and 9,000 pounds of instantaneous force into the front wall. No notched log joint could absorb that load without structural failure. The sequence of failure proceeded exactly as sacrificial design intended. The upper section of the trunk contacted the porch roof at a point approximately 6 feet from the cabin wall. The low-pitch roof offered minimal resistance. The first impact broke through the roof planking and struck the header beam. The header beam, undersized at 3 3/4 inches thick, folded under the combined vertical and lateral load. The fold occurred at the midspan, creating a V-shaped collapse that directed force outward and downward rather than backward into the wall. Dowels sheared at their designed load threshold. The angled pins broke sequentially, first the pins on the impact side as the beam folded, then the pins on the opposite side as the collapsing roof pulled the posts outward. Each shear event absorbed energy, dissipating the impact over milliseconds rather than delivering it instantaneously. Posts tipped out of their shallow sockets. The 1 3/4 inch pocket depth was insufficient to hold the posts against the lateral component of the load, especially with the dowels sheared. The posts rotated outward, pivoting on their bases, following the path of least resistance away from the cabin wall. The entire porch collapsed forward and down. Roof planks, stringers, posts, and header beam ended in a heap approximately 10 feet from the cabin's front door. The trunk itself came to rest atop the debris, its momentum arrested by the accumulated friction of broken wood and compressed snow. The cabin wall stood undamaged. No cracks in the sill log, no twisted doorframe, no structural compromise of any kind. The front door opened normally when tested after the debris was cleared. Total elapsed time from initial contact to final rest was estimated at less than 2 seconds. The entire cascade of controlled failures happened faster than a person inside could react, but slow enough that each component performed its designed function in sequence. The porch was destroyed. The cabin survived. That was the engineering specification, fulfilled exactly. Intact sill log section. Preserved sample showing no impact damage, post-event documentation, and comparative analysis across the territory. The sill log showed no damage when examined after debris removal. No splits along the grain. No compression marks where posts might have been driven inward. No displacement from its position in the wall assembly. The chinking between the sill and the log above remained intact, undisturbed by the impact that had shattered the porch 6 feet away. Comparison with documented rigid porch failures from the same period highlighted the difference. An 1886 incident at a homestead near Idaho City resulted in a front sill split along 8 feet of its length, requiring replacement of the entire timber and temporary bracing of the wall during repair. An 1887 event in the Boise Basin drove a porch post through the sill and into the cabin interior, jamming the door and requiring extraction of the post before the door could be opened or closed. The March 4th event produced none of these outcomes. The sacrificial system had performed as specified: contain damage to replaceable components, protect primary structure, allow rapid recovery. Rebuild time was documented with precision. Working alone, using pre-cut replacement posts stored in the woodshed, the occupant had the porch structure restored to functional condition in 9 hours of labor spread across 2 days. The work consisted of clearing debris, re-drilling 2 damaged sockets, fitting new posts with fresh dowels, reinstalling stringers, and laying decking. No help required, no specialized tools, no materials that had to be procured from distant suppliers. The contrast with rigid porch repair scenarios was stark. Sill replacement required jacking the entire front wall, a multi-person job requiring coordination and careful work to avoid further damage. The wall had to be supported while the damaged sill was removed and a new timber fitted and secured. Chinking had to be replaced. The door had to be refitted to the frame. Total labor time ranged from 3 to 7 days, depending on conditions and the availability of help. The sacrificial porch eliminated that entire class of problems. The worst-case repair scenario, complete porch destruction, was less costly in time and materials than the best-case repair scenario for sill log damage. The initial investment in engineered failure paid dividends measured in saved labor and avoided structural compromise. Field observations from other sites with sacrificial porches showed similar patterns. A line cabin on the Salmon River experienced porch collapse during a spring snowslide in April 1889. The porch was rebuilt in a day. The cabin required no repairs. A trapping shelter near the middle fork of the Payette lost its porch to a falling snag in February 1890. The structure was back in service within 12 hours. The method worked, not just once under ideal conditions, but repeatedly, across varied terrain and weather patterns. The engineering was robust. The principle was sound. The results were consistent. Documentation of the March 4th event spread through informal channels, trappers' conversations, ranchers' observations, correspondence between homesteaders. The story was not published in newspapers or analyzed in engineering journals. It circulated as practical knowledge among men and women who built structures in country where impact hazards were routine. The knowledge did not require endorsement from authorities or validation through formal study. It required only demonstration that the method solved a real problem at acceptable cost. March 4th provided that demonstration. Ranger Station, Blueprint Fragment, Forest Service Standard, circa 1908, Northern Rocky Mountain Region, 1890 through 1920, Adaptation and Refinement. A blueprint fragment from a Forest Service ranger station dated 1908 shows porch specifications that incorporated slip-jointed posts and shallow socket mounting. The design was not credited to any individual innovator. It was simply listed as standard practice for snow country construction. The knowledge had been absorbed into the professional building tradition without fanfare or attribution. The migration of sacrificial porch design from isolated cabins to institutional standards took nearly 2 decades. Forest Service ranger stations built after 1900 increasingly incorporated elements of the system. Posts set in pockets rather than spiked to sills, deliberate use of undersized header beams, loose-laid decking that would not form a rigid diaphragm. The adaptations were incremental, not revolutionary, each builder adding refinements based on local experience. Mining camps adopted similar principles for utility structures exposed to rockfall and equipment impact. A mill supervisor's report from the Coeur d'Alene district dated 1902 mentioned breakaway posts on ore bin platforms as a safety measure to prevent bin collapse if equipment struck the support structure. The application was different. The principle was identical. Railroad maintenance sheds in avalanche zones used sacrificial roof extensions to protect primary structures from sliding snow masses. The extensions were built to collapse, built to cleanly, directing snow away from critical equipment and allowing rapid rebuild after each event. The engineering was formalized in Great Northern Railway construction manuals by 1910. The principle spread across applications. Anywhere a structure faced unpredictable lateral loads from natural hazards, designers incorporated elements that would fail in controlled ways rather than transmit force into primary systems. The March 4th event was not the origin of this knowledge. Similar techniques had existed in indigenous construction and military field engineering for decades or longer, but it provided a documented case study that validated the approach under extreme conditions. Technical refinements appeared in professional literature by the early 1900s. Engineering manuals began specifying frangible connections for structures in hazardous locations. The terminology was formal, but the concept was the same: design for predictable failure rather than attempting to resist all possible loads. The shift represented a maturation of frontier engineering into professional practice. The method's diffusion followed economic logic. Builders adopted techniques that reduced long-term costs even if they increased short-term labor. A homesteader who spent an extra day building a sacrificial porch avoided weeks of repair work later. A ranger station supervisor who specified slip-jointed construction eliminated the need for emergency sill replacement in remote locations. The incentive structure favored adoption. By 1920, the technique had become sufficiently common that it was no longer remarked upon in field reports or construction documentation. It was simply how one built porches in country where impact hazards were expected. The knowledge had been integrated into standard practice. Modern avalanche barrier fragment, contemporary application of sacrificial design principles. Present-day continuation of engineering principles first demonstrated March 4, 1889. Modern avalanche barriers and rockfall protection systems employ the same principle that governed frontier sacrificial porches: absorb and dissipate energy through controlled component failure rather than attempting absolute resistance. Steel posts set in shallow foundations designed to bend and tip under extreme load. Catch fences with breakaway panels that tear free to prevent catastrophic overload. The engineering is sophisticated, the materials are contemporary, but the underlying logic traces back through a century of practical problem-solving. The March 4th event was not the invention of a new principle. It was a demonstration, under documented conditions, of engineering logic that builders had been approaching intuitively for generations. The significance lies not in novelty, but in clarity. The measurements and outcomes provide a clear record of why sacrificial design works and what conditions it addresses effectively. Frontier builders faced constraints that forced creative solutions: limited materials, unpredictable hazards, isolation that made catastrophic repairs prohibitively costly. The sacrificial porch emerged from those constraints as an adaptation that balanced competing demands: build quickly enough to meet immediate needs, but thoughtfully enough to avoid downstream catastrophe. The 2,200-pound trunk that destroyed a porch on March 4, 1889, could have destroyed a cabin. It didn't because someone had taken the time to engineer a system where failure was controlled rather than catastrophic. The extra hours of labor during construction paid dividends measured in structural integrity and avoided repair costs. That calculation, invest time early to prevent loss later, remains relevant in contexts far removed from Idaho Territory log cabins. Modern building codes in avalanche zones specify breakaway elements. Coastal construction standards require storm surge barriers designed to fail predictably. Industrial safety systems incorporate frangible components that sacrifice themselves to protect critical equipment. The principle persists because the physics persist. Forces that cannot be resisted must be managed. Structures that face unpredictable impacts must either absorb energy through controlled failure or risk catastrophic damage to essential systems. The choice is the same whether the structure is a lodgepole porch or a steel safety barrier. The front wall stood on March 4th. That outcome, achieved through deliberate engineering rather than luck, demonstrated a principle that continues to protect structures and lives more than a century later. The specific application has evolved. The underlying logic has not.